Last time we saw what to do if my if my c was either a constant or a polynomial, right? Let us look at what to do if my c is now exponential. So example, solve recurrence relation, solve the recurrence, recurrence, h of n is equal to 5, well, 2h of n minus 1 plus 5 to the n, and with h of 0 is equal to, let's say, 3. Okay, solution. Well, my general solution is, well, h of n is equal to 2h of n minus 1. Therefore, I don't even have to do any work here. Q is equal to 2. Okay. Therefore, general solution is a times 2 to the n. Particular solution. For the particular solution, I have c is equal to 5 to the n. Okay. Try particular solution of the form. Particular solution of the form h of n is equal to 8, well, d times 5 to the n. Okay, so if this is exponential 5 to the n, I have to try d times 5 to the n of the exact same type. Okay, therefore, what do I get? 5 to the n is equal to 2 times d times 5 to the n minus 1 plus 5 to the n, right? Therefore, 5 to the n is, d times 5 to the n, d times 5 to the n is equal to 2d times 5 to the n minus 1 plus 5 to the n. And therefore, d minus 1 times 5 to the n is equal to 2d times 5 to the n minus 1. Therefore, if I solve things around, I get dividing by 5, 5d minus 1, 5d minus 5 is equal to 2d. And solving things, I get d is equal to 5 over 3. Okay, and therefore my general complete solution, or entire solution, whatever you want to call it, I call it entire solution. Entire solution is equal to, what was it? Initial was a times 2 to the n plus 5 over 3 times 5 to the n. Now I have to solve for initial value h of 0 is equal to 3. Putting n is equal to 0, I get, therefore, 3 is equal to a plus 5 over 3. Therefore, a is equal to 4 over 3. And therefore, my solution, therefore, h of n is equal to 4 over 3 times 2 to the n plus 5 over 3 times 5 to the n. Now here's where things get slightly complicated. Well, first of all, this method that we are doing works only in specific cases where my polynomials and things are nice enough. But even then, there can be complications. So let us look at an example where solve the recurrence relation. Solve the recurrence relation h of n is equal to 5 h of n minus 1 plus 5 to the n. Okay, this time n greater than or equal to 1. And, well, yeah, that should be obvious to you guys by now. I'm just going to write h of 0 is equal to, again, 3. Okay, so similar looking problem. I have replaced the 2 by 5 here. Solution, general solution, general solution. Not much has changed. 5 h of n minus 1. Therefore, q is equal to 5. Therefore, general solution is equal to 5 to the m, a times 5 to the n, right? Particular solution, particular solution. I am going to try as before for d times 5 to the n, because my c was 5 to the n, as c is equal to 5 to the n. And you'll see I've run into trouble, because so is equal to hn, whatever. So I get d times 5 to the n is equal to 5 times d times 5 to the n minus 1 plus 5 to the n, and therefore d times 5 to the n is equal to d times 5 to the n plus 5 to the n. And that tells me my d should be 0, right? And this is a big fat no-no. So what the heck? Oh. That's a big fat no-no. And so I need to try something else. This is not working. And the reason here it's not working is this 5 is the same as this 5 to the n, right? And that's creating a problem. It's the same as the problems that I get because of repeated roots in homogeneous polynomials. And I am going to fix it by the same way. Try h of n is equal to dn plus e, dn plus e 5 to the n. Okay, so I have to again try something better. I have to include a n term in there, and hopefully that'll work for me. And now let us see what it does. Therefore, dn plus e 5 to the n is equal to 5 times dn minus 1 plus e 5 to the n plus 5 to the n, and therefore n minus 1. Oops. Dividing everything by 5 to the n, I get dn plus e is equal to dn minus 1. Where did I go? D times, yeah, dn minus 1 plus e plus e, and therefore I get dn is equal to make a mistake somewhere. Just give me a second. dn plus e 5 to the n, dn minus 1 plus e. So I should get right. Therefore, I get dn plus e plus E is equal to dn plus dn minus d plus E, right? That's why I was forgetting. Plus 1. Right, so when I divide everything by 5 to the n, I have a plus 1 from this 5 to the n. Thank God. I was going bonkers. Okay, that makes so much sense. Therefore, well, dn cancels, and I get E cancels. Therefore, d is equal to 1. D is equal to 1. I don't care about the value of E. E can be anything, right? And so I have, therefore, my solution is going to be of the form, therefore, entire solution is going to be of the form a times 5 to the n plus 1 times n times 5 to the n is equal to n plus a times 5 to the n, right? And as I saw before, the a times 5 to the n solves it, which is why this e doesn't matter. That's even if whatever value of e I take, it's going to get absorbed in this a, right? And so solving for h of 0 is equal to, what was my value? 3. I get and therefore n plus a, 0, so a is equal to 3. 0 plus a times 1 is equal to 3, therefore a is equal to 3, and therefore hn is equal to n plus 3 5 to the n for n greater than or equal to 0. Okay, yeah, so sorry about that. That took some I was confused there by my own notes. Yes, but what we have is that I have some method of how to solve the particular solutions. So general method, one, solve homogeneous part for a general solution. 2, solve for a particular solution. Solve for a particular solution. And the table you'll be using looks something like this. C and try h of n is equal to, well, if c is a constant, well, so if c is a constant, then try just, so let me say if c is some constant d, then try h of n is equal to another constant a. Okay, if it is dn plus e, then try an plus b. If it's a polynomial, n plus b, whatever. If it's a polynomial, well, dn dk x n to the k, dk n to the k plus dk minus 1 n to the k minus 1 plus dot 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 plus d0, then you should try a k n to the k plus a k minus 1 n to the k minus 1 plus dot 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 plus a0, right? If it's a polynomial above, you should try a polynomial below. If you have d to the n, so it is an exponential, try a times d to the n. Okay, so you try the same constant times d to the n. Okay, and for step 3, combine general solution, so combine general solution and particular solution from steps 1 and 2, steps 1 and 2, and solve for the initial value. Solve for initial values. Okay, so that is how you solve using HN and solving for homogeneous equations and that process. I'll do one more example where we look for, well, we solve for things using the generating function. Okay, and that will be the end of section 7.5.